looks like you can do something. You can twist, right? So your favorite topic from physics 1, torque, okay, there's going to be a non-zero torque, okay? So the net torque is not 0. This thing wants to make this rotate clockwise. We call that a negative torque. Negative is clockwise. And this is also wanting to make it torque the same way. Because even though that force is the opposite direction, it's also on the opposite side of the center of mass. So we get, there's going to definitely be rotation. That is where the action is on a current loop in a uniform field. The net force is 0. But this is where I remind you that the net force really on an extended object only tells you about the center of mass. So if the net force is 0, it means that the center of mass has to stay at rest. All bets are off for the rest of it. So what it tells us is that this loop can't, as a whole, this current loop can't just drift off toward the ceiling or whatever, but it can rotate around its center of mass. There can be a net torque. So let's go ahead and find out what becomes of this thing. This obviously won't stay in that position. It'll rotate around the center of mass. Let me go ahead and draw it a little bit further along its way. Now I'm going to draw it over here, not because it actually drifted to the right, but because if I draw it rotating in place, it's going to get really messy, right? So it doesn't actually move over here, it just rotates in place, okay? So here it is a little bit further on its rotation. Now if you're looking at that diagonal orientation and dreading the right-hand rule, you just have to remember to isolate the currents and look at this current. This current is still out of the page, just like it was over here. So the force direction is exactly the same. And same with this one. Even though the loop has rotated, those two segments have not actually changed their orientation in the magnetic field at all. What's changed is, by the way, is the front and back segment. So it might be worthwhile doing a quick slap rule on that one. So we have I, which points like that, slapping into B, short slap. I into B. So the force now on the front will be out. And you can also show that the force on the back will be in, but they will cancel. So the front and back aren't interesting. That's why I, of course, buried them not be able to draw on the plane of the page. All the action is now on the plane of the page. So, what you notice here is that this is not like a revolving door, right? When you open a revolving door, you have to stay like this if you want to keep going, right? You have to stay perpendicular. These forces are not staying that way. This is not staying like this. This force is pointing like this always. So now, you will still have some torque, but these forces are not staying tangential. So you can probably see what's going to happen is at some point, you are not going to experience any torque anymore. It's going to look like this. So I'm going to drop the front and the back from the discussion because they're really not very interesting. But now, we notice that the two forces of interest, now they truly do they've completely fallen off the tangential path. So what happens? Well, the torque is gone. The net torque is now 0. That's like if you walk into a revolving door and you only decide to push one way, like just walk in a straight line. That might work for opening the door at first, but then it gets worse and worse and worse. And then when you push the door so it's actually parallel to you, then you're not doing anything anymore. It's like this, right? I open this door, this is great, and okay, now I'm doing nothing. Okay. So what happens here? Well, it doesn't just stop dead because it's, of course, built up some motion, right? It just experiences zero net torque, but it has some inertia to overshoot. We might double check what happens when it goes a little bit past that. The forces will still act like this. These forces just insist on pointing in this direction. And so what you will find now is that what would happen with the torque there? Which way would that tend to rotate this thing? The other way, right? So if you watch here, initially the force, this one is up, this one's down, that's great rotation. Then it goes like this, and then here the force is like this. And if we bring it back like this, it'll bring it back, right? So we have this situation. So now the torque is in the other direction. These forces would tend to try to bring it back. Okay? Is there a question over there? Or are you just doing the right hand rule? Okay. All right, so there's got to be a better way to catalog all this, and there is, okay? This is really awkward to draw, as you can see, right? So what I want to suggest is a mnemonic where with a single arrow we can encapsulate everything about this. So what we can do is we can not only say where in 3 dimensions is the current circulating, but once I've established that, if the current is circulating this way or this way, I can do that with this trick. This trick is called the normal vector. So this arrow is going to represent this entire thing. Here's how. I'm going to come up with a right-hand rule, another one, a different one. I'll call that right-hand rule number 2. This is the easier one. The one that I did earlier is right-hand rule number 1. It involves 3 things. The slap rule involves slapping one vector into a second vector, and your thumb gives a third vector. This is the easier one. I call it curly straighty, okay? Because it relates 2 things, one that's curly and one that's straight. Your fingers get the curly thing, and your thumb gets the straight thing. So in my case, the current is curly. It's looping around, rectangle, circle, doesn't matter. So the curly part, if I try to draw this, I'm not even going to try. I was going to try to draw this, but that's not happening. So what happens is your fingers go around the curly thing, that's the current, and your thumb gives this thing called the normal vector. And in my case, it would look like this. It would point out of the page. Now, normal is just a mathematical word. You can't stress out too much and think it's like normal force. It's not a force. What's coming out of the page? Absolutely nothing, okay? Here's why we use it. So I wrap my fingers around the way the current goes, and my normal vector is understood to point like this. What's pointing like this? Nothing. It's a mnemonic. A mnemonic is not a physical entity, okay? Why would you do that? Well, with a single arrow, if I give you the arrow as this, that means that current is circulating this plane, and it's going around this way in the plane, not this way. So this is a stand-in for this, okay? So one arrow encapsulates a ton of stuff. So this is what you're imagining, right? When you see this arrow, think this is the current, okay? So let's go ahead and sketch in the normal vector here. So this gets a normal vector that looks like this. It's perpendicular to the entire plane of the loop. This one, it looks like this. So on and so forth, looks like this. And it looks like this. And the common theme appears to be that the normal vector actually wants to align with the magnetic field. So you notice that it experiences torque until it's aligned with the magnetic field. Then there's no torque at all there. But if it overshoots, it says, hey, I like that, and it tries to come back. Okay? So let me give you the torque formula. This is the torque on a current loop. I'm not going to derive this just for time's sake, but here's the answer. So let me start with the direction. I just pointed that out. The torque is such that the normal vector wants to align with the magnetic field. That's the direction of the torque. The torque is 0 when they're actually aligned, but otherwise the torque is such that it would want to go there. I can go ahead and draw myself. Let me just do it in a different orientation, just so it makes it easier. Let me draw the magnetic field vertically. So if the normal vector was like this, it would definitely experience a torque like that. If it was like this, it would experience a torque like that. If it was here, it would experience no torque because it's in its happy place. It would be happy aligned like that. And likewise, if you were somewhere over here, it would want to align like this. This, by the way, I drew it purposely like this because it bears a striking resemblance to what? It's a pendulum. It's an exact analog for this system. It's just like a pendulum. At the bottom of a pendulum, you experience no gravitational torque. I'm not saying the force of gravity is 0, of course, but I'm saying it exerts no torque. There's no tangential part. Over here, of course, you're going to get a lot of torque. And then in between, you'll get something in between. The analogy is exact, okay? So let's go over to the equation and see what the ingredients are. How much torque do you get? Well, how much current do you have in your loop? How strong is the field is it in? That's what's driving the torque. Oftentimes you want to accentuate the effect by not just having a single current loop, but a whole stack. So N is just how many loops you have. N is the number of current loops. A is actually the area of the loops. Area of one loop. So if it's a rectangle, use length times width. If it's a circle, use pi r squared. And I want to point out that when the angle between the normal vector and magnetic field is 90, so that angle between these two is 90, that's what it is here, right? There's the normal vector that points up, the magnetic field points to the right. Sine of 90 is 1. This is your maximum torque, which hopefully isn't a surprise, because look at how effective these forces are, right? They're entirely tangential. What angle would I put right here? What's the angle between the normal vector and magnetic field right here? 0. The theta between N and B is 0. What's sine of 0? 0. So again, no torque. Okay? So this is maximum torque on these two sides. And then that's the same as the pendulum, right? This is maximum torque. Look at the force of gravity. It's entirely tangential, right? So everything's lined up real nice. Now, you might say, wait a minute. I see a loophole. Sine of, not just, sine of 0 is of course 0, but sine of 180 is also 0. So if you had something like this, where the currents were like this, completely the opposite of this one, well then, if you do the right-hand rule on that guy, you wrap your fingers around the current, the normal vector is actually this way. It's 180 degrees to the field, right? Normal vector is left, magnetic field is right. So sine of 180 is 0, and the torque is 0 on that too. So you might say, aha, that's not like a pendulum. Well, guess what? It is like a pendulum, okay? That would represent over here, where you're anti-aligned, or what we call anti-parallel, you would also have no torque when you're doing that. But if you had a pendulum with a rigid rod, that would also technically balance, right? This should also have no gravitational torque. If you could get it perfectly balanced, it would stay right there. It's exactly like a pendulum. Of course, the big difference is, that that's very hard to achieve, right? What we do is we call this a stable equilibrium. If you give it slight perturbations, it just comes back. If you give this a slight poke, it's not coming back, it's falling over. That's the same thing here. This is a stable equilibrium. And this, I like to think of it as, it'll stay there, sure, but that's just because the normal vector wants to align with the magnetic field, and now it's paralyzed because it doesn't know what's the best way to go. It's exactly the same amount going around 180 one way or the other. So it's just paralyzed and it doesn't do anything. Unless you break the tie, of course. The forces will look like this. They will be inward. So compare these two right here. There's a big difference in how they behave. Let's try it. Let me try this top one with the forces outward. Go ahead and try to twist that a little bit and see what happens. Twist it one way. Well, like it up there. Okay. Forces bring it back. Try to twist it the other way. Brings it back, like a pendulum at the bottom, right? Let's try the other one. Forces are inward. Twist it a little bit. Okay. Falls over. Okay. So that's the behavior of a current in a magnetic field. And basically, while I skipped over the derivation of this torque rule, you can calculate the amount of torque whenever you want. You can get a number. That's not as interesting to me as you understanding the concepts. The concepts being is that the torque is 0, like this or like this. Here is this orientation that everybody strives for, so the torque is 0 and it's stable that way. This is kind of like this weirdo unstable equilibrium. The normal is actually aligned against the field, but it would like to be with the field. So if you just break the tie, it'll flip over. Here's where the torque is maximum, right? So why am I belaboring this system? Well, let me show you a way to put it to good use. So I have basically this thing here. I don't have to put it on the table here. So let me show you a couple systems that make use of the principles that we talked about today. The first I want to show you is the helical motion of charged particles. So what do I have? I have a D battery. I have a iron nail that can be magnetized. And then I have a magnet that actually makes a magnetic field. And then, just because it's going to be easier to see in the back, I'm going to put a little post-it note on the bottom of this magnet. Hopefully it'll stay on. Okay, maybe not. Okay. See if this other one has more stick left to it. Okay? And then I'm going to do is, since the nail is magnetized, and we'll talk a little bit more about what that means later, but for now, hopefully it's not shocking to you that it sticks. And then what I'm going to do is I'm going to send current through the nail. So I'm going to do that with a little piece of wire. So I'm going to attach it to the positive terminal, and I'm going to touch it somewhere here to the nail or the magnet, doesn't matter, they're both conducting. So charges are going to go up through the wire, back down and up. But guess what? These charges are not just going to go straight up through the nail. They're going to be in a magnetic field and they're going to make a helix. So instead of just going straight up through the nail, they're going to go like this. So what happens is, if I can get this centered, maybe not. This battery appears to be dead. So let me come back to that one. Let's try it with a battery that actually has some juice left in it. No. It's not working very well. I think there's a break in the conduction somewhere. Sorry. I tried this out before and it worked. I'm not sure why that's not working. Let me try another pair here real quick. Brought some backups. I'm going to dispense with the post-it. You're going to be able to see it, I think, since there's relatively few of you. This is not working at all. All right. Well, let me skip that one for now. These batteries might have some issues, so this other thing might not work. So here I put that same D battery in here so I can have access to the voltage. I'm going to send it through a current loop, and then here's a little button refrigerator magnet that's going to provide the magnetic field. And so we're going to have a chance to see this thing has a normal vector, and that normal vector wants to align with the field. So that seems to be working at least. Okay. So spinning around and around. So what is this thing? What would we call this thing? Electric motor. It's a battery, a piece of wire, and a magnet. Okay. Now, you might say, that doesn't look like a pendulum. That looks like it's spinning in the same direction. Well, that's just trickery, okay? The trickery is this. The normal vector rotates till it's aligned with the magnetic field, and then, when it would start slowing down and coming back, instead, we just turn the current off. So basically, it is like a pendulum that goes like this, and then we just let it coast, and then we let the current come back. And then it's like a one-arm motor. It's like a pendulum, and then when it would start pendulum the other way, we just turn the current off. Now, how do you turn the current off? It's really easy. If you look carefully at the axle, you'll notice that the axle sits in these things that are cupped like this. Okay? And the axle this is the wire. It actually has insulation on half of it, which means that half the time it's an electrical contact, and then when it would otherwise start torquing the other way, it just puts the insulation in between and it just turns off. So that way you can get it to rotate the same way instead of acting like a pendulum. Okay? Okay, so this battery is definitely working. So I am convinced that I can show you this other thing. It's just about as cool. So I'm going to try it one more time, and we'll see if I can get this going. Man, I don't understand why this is not working. Did I take the battery out of this one? Yeah, I have no idea why this is not working, but this is compelling. It is It goes very, very fast. Man. Huh. I don't know. There's probably just some, oh, there it is. So the helical motion, as it knocks around into the atoms of the nail, the fixed nuclei, it takes them with it. Did you see it spin? Okay, I know you're just human to me, but anyway, it's time to go. That does close the out the homework number 5. So I'll post the first lecture of homework 6 for you guys sometime in the next couple days or so. You can watch it at your leisure after the exam before we meet again.